This is it. 4.7, predicting the products of redox reactions. You'll be able to write balanced equations for synthesis and decomposition reactions and apply the activity series, the metal reactivity series, to predict the product of single replacement reaction. Synthesis and decomposition reactions. Many synthesis and decomposition reactions are redox reactions. This is a great example of that. Aluminum, solid aluminum, reacts with Cl2 or chlorine gas to produce the solid aluminum chloride. What we see happening here is aluminum with a zero charge and chlorine with a zero charge. Well, one gets oxidized and one gets reduced. So you can use your monatomic charges to predict the products of reactions between nonmetals from groups 16 and 17 and metals from groups 1 and 2, plus aluminum. Aluminum's in group 3. But if we had substituted something like sodium here or something like that, we had solid sodium plus 3Cl2 gas, we'd be able to write, or actually it wouldn't be 3Cl2, but plus Cl2, we'd be able to produce NaCl in this unique environment where we'd have all that thing going on. All right, now complete and balance the following synthesis reactions. What we have is rubidium, which is a group 1 metal. Rubidium reacts with this F2, this fluorine, to produce RbF. Fluorine is in group 7, which is going to produce a -1 ion. So in order to balance this, we're going to say 2 out in front of there, and our solid, or it is going to indeed be a solid. Okay, so I base that on, oh, and I gotta throw that there. I base that on the place where they are on the periodic table. Okay, next up is calcium, which is a group 2 metal. I'm going to say G2. And nitrogen, which is a group, it'd be group 5. So nitrogen is going to react with this calcium to produce Ca3 and 2. Okay, that's also going to be a solid. And all that we have to do to balance that is throw the C or the 3 in front of that. Just like I said. Okay, single replacement reactions. Well, what we have, these are redox reactions where zinc, in this case, zinc is reacting with ACl to produce zinc chloride and hydrogen gas. The reactants are less stable, more reactive than the reactants are less stable, they are more reactive than the products. Active metals oxidize, meaning they give up electrons very easily. Okay, so active metals transfer electrons to ions of less active metals. Copper sulfate plus zinc yields zinc sulfate plus solid copper. So what you would have here is you would have the precipitation of solid copper there. Now, zinc atoms, I said zinc atoms transfer electrons to copper ions, forming zinc ions and copper atoms. Zinc is more active than copper. An activity series lists metals in order of their activity. A redox reaction between zinc metal and dissolved copper ions is effectively what's taking place here. You put this zinc in the presence of these copper ions, and lo and behold, zinc is going to anti up and give up the electrons so that solid copper can precipitate out of here, and then the zinc exists as a soluble cation in that solution. This is your metal reactivity series. And what this shows is the list of activity, or the ease of activity from the top down to the bottom. So the most active metal would be right up here, aluminum. The least active metal would be gold. So what that means is aluminum wants to move to an Al3 ion so much more than gold wants to move to a gold 3+ ion. Okay. As a result, the inverse is also true. So these ions and their ease of being reduced. These gold ions will be reduced very easily, and these aluminum ions will be very difficult to reduce. So given all of these substances, Fe, Ag, Sn, which is tin, magnesium, lithium, and calcium, identify the most active metal. Okay, so your most active metal is going to be basically the highest on the periodic table and the farthest to the left. Now, this wasn't all what was shown on the previous slide, but this most active metal is going to be lithium. Now, the most reactive metal, what we're looking for, or metal ion, what we're looking for here is an ion, which we've got a total of 3 different ions listed. Which ion most wants to take on electrons? And the answer to that would be Ag plus the silver. Which of these is the strongest reducing agent? Well, that would be Li, because it is most easily oxidized. The best oxidizing agent is the one that is, the best oxidizing agent is the one that is most easily reduced, which is Ag plus. Now, this oxidizing agent reducing language, that always gets kind of confusing. So just keep in mind, whatever gets oxidized is the reducing agent. Whatever gets reduced is the oxidizing agent. So whatever gets oxidized does the reducing. Whatever gets reduced does the oxidizing. All right, so this last slide that I wanted to go over is writing balanced equations for any of the following pairs of reactants that will react. So what we're looking for is we're looking to see whether or not a reaction is going to take place. Now, we know that lithium ions, well, we want to compare a lithium ion to a lithium atom. A lithium atom will very readily give up electrons. A lithium ion, does that take on electrons very well? No, it does not. So this, due to the fact that this is an ion, this is no reaction. Now in question B, we see kind of the opposite. If we mix lithium with an ion, is that reaction going to take place? Yes, it is, because lithium loves to give up electrons and copper loves to take those electrons on. So what we're going to form there is Li plus a lithium ion, and we're also going to form Cu. Okay, now there is one element of this, or one aspect of this, that we do have to balance, and that is we have to balance our charges. So if we throw a 2 out in front of that Li, we've effectively balanced it, because now we have 2 lithium that give us our 2 positive charges. Okay, the next one, zinc ions and magnesium ions. This is all about which one will give up electrons and which one will accept electrons in order to become a neutral solid. Neither of these can give up electrons because they are both, they've both already been oxidized. They both lost electrons. So no reaction is going to take place there. Okay, now the next one is a little bit tricky. This is a single replacement reaction. Aluminum is a fairly reactive metal, and so what we will expect to see is aluminum to take the place of that tin. AlCl, but now we've got to balance it. We've got to have 3, because aluminum is going to form a +3 ion. It's not going to form a +2, it's going to form a +3 ion. And that chlorine, we've got to balance that out, so that's going to, we have to have 3 as our subscript there to have the 3 negative charges to kind of neutralize that. Then we've got 3 Sn, so we precipitated tin out of there. AQ. And then we've got, the last thing that we need to do is we need to balance it. We got to throw a 2 in front of that and a 3 in front of that. Okay, so we're all balanced there. Okay, the last one is E. Li solid plus Cr solid. So if you have solid lithium plus solid chromium, is a reaction going to take place? Now, just kind of visualize this. Think about it as if you have 2 metals and you kind of bang them together with one another. Is a reaction going to take place? Is something going to happen? No. There is going to be no reaction between these 2 metals. Okay. Now, this last segment was kind of tricky, was kind of tough. I would argue that this chapter kind of got more difficult as it got a little bit more abstract. What I would recommend is going back on the early stuff and making sure that I feel very, very good about that. Then, for this last little bit, these last few videos, I would make sure that I feel comfortable with the terminology of oxidation reduction. Can I identify an oxidation number? If you can identify an oxidation number in a molecule, well, then you can identify an oxidation number in two molecules. And then you can say, oh, well, it has a +3 charge here. Now it's a +2 charge. Okay, so what happened? Well, to go from +3 to -2, or sorry, to go from +3 to +2, it had to have gained an electron. Therefore, it got reduced. Once you can do that, then you can talk about, okay, if this got reduced, that is the oxidizing agent. Therefore, whatever got oxidized was the reducing agent. Okay, well, you've got this. Keep working on it. I know you can do it. If you got questions, let me know, and we will work through it. All right, everybody. I hope you have a great whatever time of the day it is. And awesome. Get out and rock and roll.